Greetings. Welcome to the project video for Main 4730 Section 2 Heat Transfer. This is Aaron Delgado and Tom Margoley. Today we will be continuing from our previous mini project. To recap the previous mini project, we had designed a cooling system for a solid-state thyristor in collaboration with Dr. Wei Singh. This thyristor has several advantages that set it apart from others, such that it had a reduced size, a lower cost to produce, a high switch frequency, and the ability to handle the high voltage for high current applications. Therefore, it goes without saying that this thyristor dissipates a considerable amount of heat from both sides, which is where the heatsink that we designed was used. For this project, and with the previous project in mind, we will be selecting a fan that meets our design parameters that are aligned with the original convective heat transfer coefficient. Then to ensure through calculations that the fan design meets the project specifications. We will also be observing if the outlet temperature is within an acceptable range for the external flow. In the previous project, we decided that copper would be the best selection for the heatsink material. The material properties were taken into consideration for the heatsink design. The characteristics of the thyristor are a height of 26 millimeters, a diameter of 85 millimeters. With those dimensions, we were able to produce our heatsink to have a fin array base thickness of 4 millimeters, a fin diameter of 6 millimeters, and with a height of 3 centimeters, with the number of the fins of 28 on both sides of the thyristor. Now, with the new objective in mind, we had to redesign our previous CAD model to allow for more effective heat dissipation. In order to do this, the model has to accommodate a fan to effectively dissipate the heat. As you can see, most of the dimensions remain the same, with the exception of the fin layout. The fins are positioned in equidistant and staggered rows where the flow of air can easily travel between the fins, both above and below the thyristor. With respect to the center of the cylindrical fin, each fin is separated by 10 millimeters both horizontally and vertically to ensure even dissipation. The layout of the fins are symmetrical about the vertical axis.
In order to begin the external flow analysis, we first had to calculate the outlet temperature of the airflow. To do this, we assumed an isothermal array at steady state temperature with constant properties, negligible radiation with the surroundings, and steady flow. Taking ambient temperature as 50 degrees Celsius, steady state surface temperature as 113.4 degrees Celsius, as calculated in Project 1, we were able to calculate outlet temperature with the following equation. The properties were taken at an average temperature of 58 degrees Celsius. This average was assumed after multiple consistent iterations of guessing outlet temperature. And T here is the number of pins in each row, and L is the number of rows, and N is the total number of pins. ST is the vertical length between rows, and SL is the horizontal length between pins in each row. With our staggered arrangement, both were designed to be 10 millimeters, as stated earlier. We assumed initial flow velocity is 10 meters per second, which is within the final range found. The final outlet temperature of the airflow was 66.87 degrees Celsius, which is not much higher than the inlet ambient temperature. This is important because we assumed uniform airflow for Project 1, and this result exemplifies this assumption. Next, we calculated the Nusselt number corresponding to our chosen convective heat transfer coefficient and found it to be 52.37, using K at average temperature from inlet to outlet. Using this value, we're able to calculate Reynolds number. C1, C2, and M were found using design parameters and an iterative process from tables 7.5 and 7.6 in the book. Once Reynolds number was found, using the equation shown, we would check if the C1 and M values reflected the calculated value. Prandtl number was interpolated at an average temperature, while Prandtl number S was interpolated at surface temperature of the fins. The final Reynolds number was 5,468.04, which corresponds with laminar flow. Maximum velocity was then calculated using the equation shown and the calculated Reynolds number and was found to be 17.37 meters per second. The inlet velocity of the air was then calculated using staggered array equation with 2sd minus d greater than st minus d. Using maximum velocity and parameters interpolated from figure 7.15, the change in pressure was calculated to be 558.1 pascals.
After careful consideration of these calculations, we were able to find a fan that met our original requirements for both the project and the heatsink. The fan is manufactured by the Mechatronics Fan Group. The required volumetric airflow was then calculated using the equations shown and was found to be 0.0025 cubic meters per second or 0.15 cubic meters per minute. The power required for airflow across the fin array is directly proportional to the static pressure difference, which was again calculated to be 558.1 pascals. Using the datasheet provided, we found that the PFR 0912XHESP00 meets both volumetric airflow and pressure parameters for our design.
Lastly, we looked at how convective heat transfer coefficient changes with volumetric flow rate and power. Using the equations given in Engineering Toolbox, we were able to find the correlation between volumetric flow rate and power, and then use these parameters to work backwards, finding velocity, maximum velocity, Reynolds number, Nusselt number, and then convective heat transfer coefficient. To make this process easier, we used Python and derived the following graphs. As you can see, convective heat transfer coefficient is proportional to the 1/3 power. While there is almost a 1-to-1 correlation between convective heat transfer coefficient and flow rate.
In conclusion to this project, we ensure that the fan did indeed meet the design parameters of our original convective heat transfer coefficient. We've also confirmed that the new design and fan met the project specifications. We have determined that the outlet temperature is within an acceptable range for external flow. We've also determined that the convective heat transfer coefficient as a function of its power was obtained through the calculation of volumetric flow rate. When it comes to the cost of purchasing the fans and the material, it is the wiser choice to purchase the available bulk in units of 250, which saves approximately $13 per fan. To purchase the complete set of fans and copper material based off the national price of copper, and if the production is considered, the total cost would be $5,832.83 or $23.33 for just one. And finally, based on the fan power consumption of 44.4 watts, the daily price for 24 hours of continual use is 12 cents per day. Thank you very much.
Please refer to our references. Thank you so much.